Okay, welcome everybody.
That's already
So Matt asked me to say a word or two to get things started. So yeah, so this is our first UQM virtual seminar, kind of an experiment. So thanks to Hassan for getting everything organized, and to Matt Lapa and Hassan Shapurian for volunteering to sort of test this out as our first speakers. Sorry, I don't have your titles in front of me, so I'm not really going to give a proper introduction. But I just want to suggest that everybody who's not speaking probably turn off your video and then also mute your microphone. But if you have a question, then it should work to unmute your mic and then ask the question. I think you just need to shout into the microphone. Maybe Matt can can give some guidance what he thinks is working for him as we go. Okay, so thanks everybody for being here, and with that, I'm looking forward to hearing from Matt.
Okay, so I'll get started. I'm going to share my screen, and if you have questions, I think you should just interrupt, and then you should also let me know if I'm not loud enough. So first, can everyone see the PDF of my talk and see the mouse moving on it?
Yes.
Okay. All right, great. Then let's get started then. Okay, so I'm going to talk about work in progress with Michael Levin. And this is about the problem of topological superconductivity beyond mean field approximation. So working in theories which have a full U1 symmetry of particle number conservation. So here is the outline of the talk. So I'll give a brief background on topological superconductivity and this problem of particle number conservation. Then I'll just give a lightning review of standard mean field models of topological superconductivity. And then I will discuss our number conserving model, and finally present rigorous results on the model, and then discussion and some open questions. I see people are saying things are a bit too loud. Let me see what I can do about that. Maybe if I talk a little quieter, does it seem better? Not sure I can turn the mic down. Okay. All right. Okay, this seems good. So back to the talk. So to start, so we all know that topological superconductivity and Majorana fermions have been of great interest in condensed matter for almost 20 years now, since these original papers of Kitaev and Reed and Green. Most of the interest is related to using these systems as a platform for quantum computation. And even private companies like Microsoft are pursuing this specific route towards building a quantum computer. One issue is that most studies of topological superconductivity rely on a mean field approach to describe superconductivity, and this violates particle number conservation. So in mean field theory, you work with Hamiltonians that only have a Z2 symmetry of fermion parity, and their eigenstates are superpositions of states with different particle number. But on the other hand, we think that real systems always respect particle number conservation, and there are old approaches to superconductivity and superfluidity due to Yang and Penrose and Onsager, which explain how to characterize superconducting or superfluid order using a wave function with a fixed number of particles. And so recently, Anthony Leggett and others have argued that this violation of particle number conservation may pose a problem for Majorana-based quantum computation. So let me explain in more detail what Leggett's concern is. So we know that the mean field approach can describe thermodynamic properties of superconductors pretty well, but these are controlled by the energy spectrum or the eigenvalues of the Hamiltonian. And that's just because you use the eigenvalues to compute the partition function, and then you use the partition function to compute thermodynamic quantities. But for quantum computation, you actually need a detailed understanding of the eigenstates, for example, to understand Berry phases. So in topological quantum computation, the gates that you perform on your qubit are usually actually equal to the non-abelian Berry phase for some adiabatic process that you're doing on the system. And so you need to be sure that you understand the eigenstates well enough to compute that properly. So Leggett's basic question is, does mean field theory capture the properties of the eigenstates of the system that are crucial for quantum computation? Is there a question? I hear some noise. Okay, maybe not. So this is the basic question, is whether the eigenstates are captured well enough by the mean field theory, or if there might be corrections to things like Berry phases that you might compute in mean field theory. So let me give an example of something that can go wrong where mean field theory can fail to capture some property of the eigenstates. So I've shown here, consider two systems, system A and B, which interact in such a way that there's a total conserved particle number, Na plus Nb, but particle number of system A is not conserved and neither is the particle number for system B. And suppose very generally that at time t, this entire system is described by some density matrix, rho of t, and that this density matrix commutes with the total particle number operator. Then if you define the reduced density matrix for system A, you can prove that rho of A commutes with the particle number operator for system A. Now, on the other hand, if you imagine that system A is a one-dimensional wire and system B is a bulk superconductor, and you try to forget about system B and just model system A with mean field theory, then you would find that this theorem is violated. And that's just because the mean field eigenstate is a superposition of states with different Na eigenvalue. So let me outline our approach to this problem. So what we'll do is look at a toy model of topological superconductivity that respects particle number conservation. And we'll try to rigorously determine when this model possesses the properties of the mean field models, the properties that are desired for quantum computing applications. And I'll mention now that this amounts really to proving stability of a topological phase to long-range interactions, because we'll see that including the effect of number conservation, and this simple model ends up incorporating long-range interactions into the system. And I want to contrast our approach with some previous work on this problem of particle number conservation and topological superconductivity. So previous work, there's some work using low energy field theory descriptions and bosonization and various approximations. There's other work using special exactly solvable models or models with extra discrete symmetry which can protect certain degeneracies. But here our approach instead will be to write down a fairly simple model which is physically reasonable but which doesn't seem to have any exact solution. But then we'll try to make rigorous statements about the model and in a broad, in a wide area of the parameter space. So we don't want to have results that depend on fine tuning of some parameters. So now I'll just start with a brief review of the usual mean field models of topological superconductivity. So this is the Kitaev P-wave wire model. So it's a model of spinless fermions, Cj, hopping on a wire of length L. I've written it with open boundary conditions, and you can see it consists of a nearest neighbor hopping term, a superconducting pairing term, which is of course the term that violates particle number conservation, and then a chemical potential term. And the physical picture you should have in mind, and which also corresponds to the experimental setups which are being built, is that you have a semiconducting wire which is sitting on top of an S-wave superconductor that's supposed to induce superconductivity in the wire. So if you look at this model at a special point, so it's easiest to see the properties of this model at a special point where t equals delta and mu equals 0. So here you can diagonalize this Hamiltonian in a basis of Majorana fermion operators, A and B defined here. And if you look at this model at this special point, you see that in the bulk of the chain, the B Majorana from one site is interacting with the A Majorana from the next site, but at the ends you have these unpaired Majoranas A1 and BL, and they don't appear in this Hamiltonian. So they actually commute with H, and then as a result you end up having two degenerate ground states labeled here as plus and minus. These states have fermion parity plus or minus 1. Then this model also has an energy gap equal to delta above these ground states. And then it turns out that you also have a long-range correlations in these ground states. So if you take the expectation value of this product I times A1 times BL, it's equal to the fermion parity of the state. And the thing to notice about this is that this correlation function stays finite even as the length L of the wire is taken to infinity. And from this correlation, you can derive various known properties of these mean field models, such as this teleportation effect, and also the 4-pi periodic Josephson effect. So this long-range correlation is a sort of more fundamental property that is related to those effects. So let me just now summarize some of the properties of this mean field model for general parameter values. So the topological phase of this model exists for when the absolute value of mu is less than t and when this superconducting pairing delta is non-zero. And in this phase, you have a unique ground state and a finite energy gap in a sector of fixed fermion parity. And then you also, the two lowest states, which have opposite fermion parity, are nearly degenerate. And then you also have this long-range correlation between the ends of the wire. So here I've drawn a cartoon of the spectrum of this model in the sectors with fermion parity equal to 1 and minus 1. So you see there's always a unique ground state and then a finite gap to the excited states. But then you see there's also this gap delta P between the even and odd parity ground states. And in this mean field model, what you can show is that this gap is actually exponentially small in the length of the wire. And this is essential for the utility of this system for topological quantum computing, because you have two nearly degenerate ground states which are then separated from the rest of the states by a gap. So these are the type of properties that we want to look for in number-conserving models. So let me explain our model now. So the model, again, the physical picture to have in mind is a wire sitting on top of a bulk superconductor. And now what we'll do is add in degrees of freedom to represent this superconductor. So what we do is incorporate additional degrees of freedom n and phi, which are number and phase operators with the usual commutation relations. And this lowercase n physically counts the number of Cooper pairs in the bulk superconductor. And so our model will have a total conserved particle number, capital N, which is equal to the number operator for the fermions on the wire plus twice this lowercase n. And then, of course, e to the I phi adds a Cooper pair to the superconductor. So the Hamiltonian for our model consists of two terms. So the first term, H naught, looks like the usual mean field Hamiltonian, but it just has this extra insertion of e to the I phi. And so the physical interpretation of this is just that when two fermions leave the wire, they enter the superconductor as a Cooper pair. And H naught on its own would be almost trivial, but we also add in the second term V, which represents a charging energy for the superconductor. And this charging energy is written in terms of lowercase n, not the full conserved particle numbers. So this adds very non-trivial dynamics to this model. And crucially for our results, this charging energy, capital EC, is chosen to scale as 1 over the length of the wire. So this is the correct physical scaling of the charging energy of the superconductor if its size is about roughly the same as the wire. So the true parameter here is actually this script EC, and all our results will be stated in terms of that parameter. And of course, this model commutes now with the total particle number, which is the sum of the number on the wire and twice this lowercase n. So let me point out one sort of subtle aspect of this model. So suppose we go to a sector of fixed total particle number equal to m. In this sector, if you can rewrite the charging energy in terms of not lowercase n, but in terms of the number operator on the wire. And if you do this, you'll see that this charging energy term prefers the wire to have a filling equal to this combination m minus 2nc. And in general, this filling is not the same as the filling that's preferred by the chemical potential in the H0 part of the Hamiltonian. So there's actually this second effect that this charging energy term is having. So in addition to just turning on this charging energy term, which is one effect, you have this additional effect of tuning the preferred filling of the wire. So you actually have to take into account both of these effects when you analyze this system. So this model should really be thought of as a 2-parameter deformation of the mean field model. So there's really one parameter in the game is just the magnitude of this charging energy, but there's a second parameter, which is actually how different this m minus 2nc is from the filling that's preferred by the Hamiltonian without charging energy. So today, just to give a flavor for the physical content of our results, I'll present the results in a simple case, which actually avoids that subtlety that I just mentioned. So we'll look at a simple example where we'll always fix the total particle number equal to m and work in that sector. And then we'll look again at this special point t equals delta mu equals 0. So in the mean field case, this was where the Majorana fermions at the boundary completely decouple from the bulk. And then we'll also tune this parameter nc, which remember appeared in the charging energy as some constant. We'll tune it to this particular value so that m minus 2nc equals L over 2. And what this is actually doing is avoiding that competition I mentioned on the previous slide. So here's our first result on this system. So this has to do with the energy gap of the system. So recall that in the mean field case, if you fix the total fermion parity, then you have a unique ground state and a finite energy gap. So this theorem is telling you that in the number conserving case, if you fix the total particle number, then you also have a unique ground state and a finite energy gap. So in particular, if this script EC is less than 4 delta, then the full Hamiltonian has a unique ground state in the m particle sector, and the energy gap of H within the m particle sector is bounded from below like this. And this result holds for any system size L. So you can see that as long as this condition EC less than 4 delta is satisfied, the gap in this system stays open. So the next result has to do with that long-range correlation between the two ends of the wire. And to explain it, I first need to back up and tell you about a property of this number-conserving model without charging energy. So it turns out that at these special parameter values, t equals delta, mu equals 0, this Hamiltonian H0 commutes with Majorana-like operators. So these take this form. So you can see that they almost look like the ordinary Majorana fermion operators, except they have this insertion of this phase operator. And so, for example, A1 dagger always adds a particle because C1 dagger adds a particle, C1 removes 1 particle, but E the I phi adds 2. And similarly for BL. But if you take their product, A1 dagger BL, this operator is actually Hermitian, and it does square to 1. So this is the analog in the number conserving of IA1BL that we looked at in the mean field case. And if you consider this Hamiltonian without charging energy, and you look at its ground state in the M particle sector, then you have an identical long-range correlation as in the mean field case. So our next result has to do with showing that this correlation survives in the full model with charging energy. So here's the second theorem. So recall that in theorem 1, we showed that under certain conditions, you have unique ground state and a finite energy gap. So let's choose this charging energy so that theorem 1 holds. And then let psi naught be the unique ground state of H in the M particle sector. Then you can prove this lower bound on this long-range correlation function. So here there's a factor of -1 to the M, that's the fermion parity. Then you have this correlation function. And it turns out you can bound it from below by some function which is positive for a sufficiently small charging energy, and then plus terms that go to 0 as powers of 1 over L. So this tells you that this long-range correlation
Can I ask questions?
Sure, yeah.
Yeah, okay, so the capital A and capital B, so what's the algebra of themselves actually? So can I see, so capital A and B, they are still complex fermion operator, is that right? Or?
Yeah, so they satisfy actually the type of anti-commutation relations of complex fermions. They're actually Hermitian, though, up to a phase. So if you take BL dagger, it'll be equal to E to the I phi BL.
Yeah, but then the anti-commutation of A and A dagger would still be 1, or?
I think it is still 1. Yeah, it turns out that the factors of the phase cancel each other out when you do that calculation. Yeah.
Okay, so the standard fermion statistics or something will still work on A and B.
Right, right. Okay, so these actually appeared in the appendix of a recent or semi-recent paper by the Station Q group. So this is the second result. So now let me just give some general discussion of these results. So I presented the results in a very special case, but actually we can prove similar results for very general values of all of the parameters appearing in this Hamiltonian, as long as we assume that T delta and mu are within the bounds of the mean field topological phase. So as long as absolute value of mu is less than T and delta is non-zero, then there's a very large range of all these parameters where you can prove stability results like this. And one thing about this model is that it's actually very non-local. That's because this phase operator is coupling to all the fermions on the wire. So usual methods that you might use to prove stability of topological orders to perturbations actually don't apply to this model. So methods based or that rely on Lieb-Robinson bounds actually don't work here. So instead, our proofs actually, they're tailored for this particular problem, and they use the positivity of the charging energy term. And they also use the fact that if you have a 1D mean field model of superconductivity, then the fluctuations of the particle number are actually fairly small. They scale as the square root of L. More generally in BCS theory, it's a well-known result that the particle number fluctuation scale is the square root of the system size. And so the proofs are actually all variational, and they use as a trial state the ground state of H naught with some chemical potential mu prime. And turns out that it's very useful to choose this mu prime not equal to the chemical potential that appears in the original Hamiltonian. And that's because of this issue I mentioned about the charging energy competing with the preferred filling by the original chemical potential. So it turns out you can choose a trial state with a different chemical potential to compensate for this, and then you can prove results like the ones I showed. So for future work, realistic proposals for Majorana-based quantum computation always use 2 wires. And this is because if you just have one wire, then the two low energy states have opposite fermion parity. And it's believed that there's a super selection rule which states that you can make a quantum superposition of states with different fermion parity. So those two states are not useful to form a qubit. But if you have two wires, then you can fix the total parity and you still have two degenerate states. And those are the states that you want to use for your qubit. And in the mean field case, you can still prove that the splitting of those two states is exponentially small in the system size. Now, for the number conserving context, you would still want to use, again, two wires, but now you go to a sector of fixed total particle number. And so here again, you can use our same methods to show that the gap will stay open and you have two approximately degenerate ground states. But the question is, what exactly is the splitting of these two ground states under different kinds of perturbations? So is it still the exponentially small splitting that you want, or is it some bigger splitting that maybe goes as something like a power law of the length of the system? And although we expect that it's exponentially small, it turns out that all the methods usually used to prove this rely on locality properties of the Hamiltonian, which are not present in this system. So this is the problem that we're working on now. And with that, I'll end the talk, and I believe there's still a few minutes for questions.
Hello, can I ask a question?
Yeah.
Okay, hi. Yeah, I just had a question about, so I guess one intuitive way I can understand the setup here is that we have the gapped fermionic degrees of freedom, and we're coupling them to some gapless bosonic degrees of freedom, right? The phase field. In some sense.
Yeah, well, it's not necessarily gapped though, because it's this phase doesn't vary locally or anything. It's not necessarily gapless, this phase degree of freedom.
Right. I guess you're mimicking the gaplessness with this 1 over L term in the Hamiltonian, perhaps. But the point or the question I wanted to make is, so at least the fermionic degrees of freedom should still have exponentially decaying correlations, right? That's somehow in some sense, the fermionic degrees of freedom are still gapped. So I would imagine, could one not use that gappedness to argue stability against coupling it to this field?
So the thing is that, say you know some system has a gap, and then you want to prove exponential decay of correlations. An intermediate step is to use the locality of the interactions. And that's not present here. So that's what makes some of these results a bit more difficult to show. And
okay, even if one says that if one introduces an extra ingredient, the fact that you want to look at a correlator of an object that's odd under fermionic parity, and maybe using the symmetry sector, one might be able to say that it has to be exponentially decaying.
Yeah, so for example, if you look at the paper of Hastings and Coma, where they prove decay of correlations in gap systems, so you assume the gap, and then you assume some locality property of the interaction. So for example, you could assume that they're short range or exponentially decaying or power law decay. And then the type of decay you'll get for the correlation actually depends on the locality property of the interactions in the system. So that's a necessary ingredient for going from knowing that there's a gap to proving the decay of the correlation function. So that's the issue here, which is that we don't have a Hamiltonian with nice locality properties.
Right. Okay, just one last question. Oh, sorry.
Let's see if there's any other question.
Okay, sure.
Okay.
Sorry.
No.
I think we booked this room till 3, so.
Oh yeah, that's not.
That'll be on time. All right, then if there is no more question, let's move on to the next talk. So my name is Hassan Shapurian. I'm the second speaker of today. Let me stop my video. Let's see. Okay. Actually, I think